presentation of video completion conditioned by natural language-based descriptions, which is a mouthful title, which explains a simple proposition. How can we use deep learning techniques to turn images to life? Now, one second. Now, in this presentation, I'll try to outline the problem that the statement of the problem that we're trying to solve and how is it relevant. Then I'll offer a short synthesis of the related work of the literature approaches to solving this task. And then I'll focus on our proposal of and our solution to this problem, and discuss our results, the limitations and challenges that we faced. Now, what is text-guided? To understand what text-guided video completion is, we need to get a broader overview of generative AI as a domain. We can specify different subdomains of generative AI based on the goal that we're trying to achieve. So we can delimit either image synthesis, video synthesis, or even text synthesis, which is very popular nowadays with tools such as ChatGPT. Well, this problem comes as a mix between several subdomains. What we're trying to do is that, given a source image, we want to predict the temporal progression of that source image, but basically create an animation. But that animation should be conditioned by a natural language description. So we want to transform an image into a video, but we want to also tell the algorithm how we want to create that video using the textual language. This has several applications, which I've listed here in different areas: entertainment, gaming, VR, AR. It all comes down to the fact that such a technique may prove useful as a cost-efficient alternative to complex rendering mechanism in different animation requirements, be it either gaming or VR or even movie making or all sorts of animations, and even in education and training purposes, such as building specific scenarios to better understand different practical settings. Now, I'll try to explain the overall literature approaches to solving this task, and I'll start by introducing this text video prediction. This is the first serious paper which proposes a method of solving this task. It was introduced last year in August, if I'm correct, and it aims at solving a very simple edge case of moving digits from left to right, more commonly known as moving list, in a grayscale settings, or perhaps some very simple objects, and we can see it's not performing so well. So the key takeaway is that this is a very, very challenging task. We haven't had any significant solution until last year to solving it. And we can see how we can mark this as the beginning of it. Next, I'll talk about Tell Me What Happened, which is the current state-of-the-art technique in this area. It was introduced by researchers at Meta at the end of last year. And they propose a multimodal masked architecture, which basically means a couple of simple things. Multimodal represents the fact that it's able to solve multiple tasks. So it's able to predict the future, but also rewind the past or provide an infilling, which is an interpolation between two individual frames. It can predict the content between those two frames. The way they trained this architecture is by taking millions of samples of videos and masking different parts of those videos. So they masked either a couple of frames or parts of individual frames, and they trained the model to reconstruct the missing parts using a combination of all sorts of vector quantized encoders and decoders and some pretty complex architecture. Next, we have DreamX, which was proposed by researchers at Google at the beginning of this year. It's also a multimodal architecture because it's also solving different tasks, such as video editing. It is capable of editing the contents of a video based on your language description, but it's also performing image to video, which is the task that we are discussing. It's using video diffusion models, which will go in depth later on. But it has very good performances in terms of quality generation. They are very realistic, and here we see how versatile it can be in terms of generation. Here we have a spreadsheet of controlling different hyperparameters and the results we get for a prompt of orangutan taking a bath or something similar. Now, to understand our approach, I'll try to offer a very short and concise theoretical background to the deep learning techniques that we employed. So when it comes to generative AI, since 2014, the focus has been on using different GAN architectures, which are generative adversarial networks. But in 2021, some researchers showed that a totally different architecture is able to outperform GAN, the best GAN models that we had at that time, on the task that they are actually the best at, which is image synthesis. Now, we'll try to offer a very simple explanation of how diffusion models work, because we also use diffusion models to solve this task. Now, a diffusion model is very similar in approach to an autoencoder. It has two parts, an encoding part where it processes data, and a decoding part. Now, the encoding part is called forward diffusion, and the objective of it is to take large portions of data. In this case, we take an example of images, and corrupt that data by continuously adding Gaussian noise. The purpose is to add more Gaussian noise step by step until we fully corrupted the data. Why we would do that? Because then we have the reverse process where we try to remove Gaussian noise step by step, so that we recover the original data. Well, why would we do that? Because in these two diffusion processes, we actually define two probabilistic distributions, which are conditioned differently. Here we can see Gaussian distribution conditioned one way, here another way. And by some clever mathematical manipulations, we can obtain basically two Gaussian distributions which are conditioned in the same way, and then we can try to do what we always do in machine learning: minimize the loss. So basically, we want to minimize the divergence of those two distributions, and here we can see a close form of how we would express that. Basically, the training objective would be to learn this function mu theta. Now, this can be even more simplified by expressing this function in terms of the current sample and epsilon, which is actually the noise added at that step. So we can actually, instead of learning this complex function, we can focus on learning this function epsilon theta. And to understand what that represents, we will use this example. This function is actually describes how much noise to add to a sample xt. So this equation is applied, this formula is applied on every individual step in this case. So the model predicts how to remove the noise for step 7, and using this formula we generate step 6, and we apply this recursively until we remove all the Gaussian noise and we have the final sample. This is diffusion models in a nutshell. There are more complex aspects when we talk about different conditioning mechanism, but in a way, that's what all of them do. Now, there are several architectures which use diffusion models to perform all sorts of synthesis. I'm sure you may have heard of DALI, perhaps, or Midjourney, or perhaps even Stable Diffusion, which we chose to present today because it's a backbone that we used in our architecture. Stable Diffusion is a bit different in the sense that instead of dealing with pixel images, as noted here, we use the latent space. The latent space is an algebraic reference space. It's basically a way in which we compress data. This helps a lot in reducing computational complexity. So what happens is that we take an image and we encode it into a vector, which is less computationally expensive. And then we apply all sorts of diffusion processes on those latent representations, and then decode the final result, and thus we get another image. Now, we note here that this is the architecture diagram of Stable Diffusion, and it allows for different conditioning mechanisms, but we'll focus on text. So to understand our approach, I have prepared a step-by-step explanation, a visual explanation of how it works. So let's say that we want to generate, first of all, just images. For a prompt, something like a cat wearing Mexican hats. We would sample random points, which constitute that original Gaussian noise. So these represent the sampled latent start points. And we would apply the backward diffusion process, and that will generate a trajectory in the latent space. So we can see here how choosing different start points leads to different results. After applying the backward diffusion and finalizing all the steps, we are now left with a latent representation, which is then decoded, and we get different images. We can see how diffusion models tend to map similar data into forms of clusters. So similar images are somehow close together in this latent space. Now, when in our case, we actually have a source image. We have a start point, so to speak, sorry. Now, what we would do is we would take the original image, encode it into the latent space, add Gaussian noise to it, and then we would basically have another start point on which we can apply backward diffusion. But this naive approach would not lead to sufficiently good results, because the diffusion model, due to its learned distribution, will skew the trajectory towards what it has previously learned. So although our result might respect the conditioning text very well, we would lose a lot of the spatial features of the start point. So the goal of our project is to recover the original trajectory during the backward diffusion process, so that we maintain most of the spatial features, but also respect the conditioning prompt. That is the goal that we had in mind. Now, in order to achieve that, we use a different inversion scheme called null text inversion. It is a very complex mechanism, but I'll try to be concise about it. The way it works, we see here that by just inverting an image and then applying backward diffusion will lead to a different result. What we want to do is that for each step, we actually perform some pivotal tuning to recover the forward trajectory. So by using such a mechanism, before that, I'll show why it was used. The authors proposed this different inversion mechanism to perform image editing, which is in a way similar to what we try to achieve. And here we can see how naive inversion does not reconstruct the original image, but the null text inversion is able to fully reconstruct the image. Next, with some clever manipulations of attention mechanism, we can actually perform editing using the original trajectory recovered with this inversion. So we can perform different editing techniques on it. Now, our method is represented in this diagram. Given a source image and a text prompt, we will apply null text inversion to encode the original image in the fully noised Gaussian representation. Then we'll apply a short backward diffusion to a time step t0, where we apply a warping function, which changes the global scene, perhaps moves the camera on X and Y directions, so that we generate more latent representations, each latent corresponding to one frame. Next, we again add Gaussian noise so that we introduce more freedom in the spatial special features representations. And then we continue the backward diffusion, recovering the original trajectory up to a time step t1. At this point, what we actually do when we realized it might be better to let the model perform the trajectory on its own without intervening on the trajectory path. What this does is that it boosts the text conditioning signal. So it allows the output to be more to correspond better to the conditioning prompt. And in the end, we just decode the latent representations and we get the next frames, which are temporally consistent. Yeah, for the backbone of this method, we used some existing approach to performing this video generation, which is able to solve that task in a zero-shot context. And thus, we also inherit that nature, which means that we actually don't need to train our model on any video data. We use a pre-trained text-to-image model, which is very general and robust, and we manipulate the latents in such a way that we are able to convert that output to videos. To evaluate our method, we followed the protocol of the current state of the art, which uses several datasets. We chose kitchens. This is a dataset with many videos where people perform different daily activities in the kitchen, annotated with various captions. It has about 100 hours of videos. It was taken with about 40 participants all over the world, and it's used as a benchmark for many different tasks, such as video captioning, object detection, and the like. And we perform a quantitative evaluation of our method in comparison with the current state of the art. In order to evaluate the method, we use these metrics. The 3D SSIM, which is the 3D Structural Similarity Index, is an extension of the original Structural Similarity Index, which is able to evaluate the similarity between two videos, because it is able to consider a video as a 3D image. So we apply the median of that score. Next, we also focus on the peak signal to noise ratio, which compares the quality of the generated videos to a form of corrupted videos. And very importantly, the Faircade video distance. This is a metric which compares two collections of separate videos. It creates a distribution of the ground truth videos and the distribution of the predicted videos, and it compares the embeddings of those two distributions. And we used the publicly available checkpoint of the state of the art, which was pre-trained of this dataset. The state of the art produces videos at a resolution of 128. Our method works with a higher resolution of 512. So we evaluated the predictions in two separate methods, either by resizing our output to the original ground truth or by resizing the ground truth to our output. And we noticed that our method, despite no training on this dataset, it is able to achieve comparable results with the state of the art. Yes, that would be it. We also show here as a qualitative evaluation how robust the method is, because of the pre-trained text to image, we don't need any training on any other data. And we tried to offer a few examples which are pretty different. We have a horse galloping on clouds, or a bear waving hands, or simply just some clouds moving on the sky. And besides that will be about it in terms of evaluations. I'll discuss now some limitations and challenges of our method. It is very computationally expensive, and this is because of the diffusion models employed. They are naturally very consuming in terms of memory, but also especially in terms of time performance, because their nature is iterative. So there, we can perform any parallelization during the sampling process. Each step is iterated one after another. So this is a drawback. It's pretty computationally expensive. And we faced several challenges in achieving temporal consistency, especially during long video generation. While our method focuses on 8 to 16 frames generation at one time, we are able to perform long video generation by employing an autoregressive nature. So the model infers multiple chunks, each conditioned on the previous one. This again introduces more computational complexity. And as with any generative AI task, there are several ethical concerns involved. Because as these generative tools become better and better, there is higher and higher risk of misinformation, risk of trust. And we believe that by researching this topic, we can actually better understand the dangers of it and define different mechanisms to protect against it, such as high performance detection mechanism or perhaps regulatory support. Yes, thank you so much. That is our presentation. That is the presentation. And if you have any questions, feel free to ask.